Hi, we're going to take a look at the air conditioning plant in this module. The air conditioning plant in the simulator represents what you might find inside of a building in terms of being able to supply hot and cold water, air to supply to a building. Let's just talk through the system. So we have air that is brought in over here. Right now I'm simulating summertime conditions, so 30-degree temperature, 90% relative humidity. And it's going to cycle through and it gets to this portion where it has two different operating modes. The summertime operating mode is going to be this pathway, which passes by my refrigeration plant, which allows that air to be cooled. It then circulates using a fan, and we have a heater in our system, and then it makes its way to two spaces. Air then cycles out and leaves the system, and new air is drawn in. I also have the ability to recirculate air. Okay, so I could adjust some dampers, which would give me the ability to recycle some air. For now, I'm going to leave it at 100% open. We notice in our accommodations it's hot, 40-some degrees, so let's work at getting our system on. In order for this thing to run, I'm going to need to supply a few inputs. My refrigeration plant is going to need to reject heat, and that's done by cooling water. My heating system, so I have a heating system and I'm going to supply steam to that. This mode I'm not going to use in the summertime, but I'll need to supply it anyways, which is fresh water that could be used for humidification. So I'll open that guy up and we'll see that my plant is ready, and I'm going to turn it on. Okay, so we see we're drawing in air and it's entering into my system. My refrigeration plant is running and it is cooling the air. And then I have a little heater that is bringing my air to my desired set point. So in this case, I have it set to exit my system at 25 degrees and 50% relative humidity. That air then makes its way into my accommodation and my control room, and then will leave. You'll note that because I'm supplying air to multiple spaces, I am not able to hit 25 in each space. So I may have to adjust some of my inlet dampers to adjust the flow into either space. So potentially I might want to increase the airflow into my control room if I'm looking to balance out these spaces. Your spaces are always going to have to be adjusted on their own, either through automatic dampers or manually, because the heat load is going to change in each space. So depending on the occupancy, what the equipment is in the space, you may need to balance out these systems on an ongoing basis. Okay, so grab your pen and paper. We're going to take down a little bit of data before we move on to our next phase. Okay, so what we're going to do is we're going to mark down our temperature and relative humidity as we pass through our system. Okay, so it looks like we're going to start at 30 and 90. So 30 degrees and 90% relative humidity. As we pass through, we're going to cool. So we're going to cool, and the heat that's being remove 258 or so kilowatts. After the cooling process, it looks like we are sitting around 13 degrees, 13.5 degrees, and 100% relative humidity. Then we're going to heat, so 58 Q, about 58 kilowatts of heating, and that's going to bring us up to 25 and 50%. Okay. So just while we have that data, a couple things to change before we move on. So one of them is if we open up our bypass dampers. So right now we are bringing in 100% air, and that passes through my system and then leaves. If we just note what's leaving our system, it's about 27 degrees and 40% relative humidity. The air that we're drawing in is 30 and 90. This air is a lot closer to our set point. So it's going to be easier for us to maintain that air back to our set point in terms of energy consumption than it is for new air to come in. So let's take a look what happens when we change our dampers. So say if I went to 50%. Now we're blending the outside air, which is far away from our set point, and the recycled air, which is closer to our set point. And so what we can see is that our heat requirements, our energy requirements, have changed. We had 258 in terms of our cooling load. Now we're at 170. So that's a great improvement. The heating load is about the same, so that didn't change. However, the total energy has gone down by 90 or 100. So we've had quite an improvement in our energy requirements. Generally, we're going to want to recycle some air to minimize our energy. Sometimes, though, if we do it too much, we are going to recycle stale air, lack of oxygen. So we may be hesitant to commit 100% to our bypass. So always we want to have some fresh air in. The more fresh air you have in general, the more energy it's going to cost you to condition your space. Okay, I'm going to just send it back to 0. And we're going to switch over to looking at a heating scenario. Okay, so I'm going to change the outside conditions. So my ambient air temperature, I don't know, let's say I'm going to change it to say -5, and maybe it's like 60% humidity. Okay. So if we go back to our simulation now, some things have changed. So my inlet air has now changed. And my operating mode has changed. So I have this damper here, which was in a different position earlier. Now it's switched so that it's moving through in my winter side. Okay. This would take a while to adjust. I have the simulator running fairly quickly in order to allow us to have the changes happen with very little interruption. Okay, so let's look through what happens now. We bring in cold air from outside. It goes through a heater section. It then goes through a humidification section. And then we have a final heating to get to our comfort conditions. Okay. Once again, depending on heat load, we may not hit our targets in some of these areas. Okay, so heat losses and heat gains may not mean that we get the right temperature in either space. So once again, you may need to adjust your dampers, adjust your set points so that ultimately you can get to comfortable conditions inside of your spaces. Air leaves after changing its conditions a little bit and exits out. Normally I would have some recirculation through the bypass. However, for this scenario, I'm just going to leave 100% makeup. Okay, so let's just gather some data. So my air is going to come in at a temperature of -5 and relative humidity of 60%. It then goes through a heat process. So Q there, 127 kilowatts. And that brings my temperature up to 19.5 degrees and my relative humidity of 11%. I then go through a humidification process. It drops my temperature down to 19 degrees and relative humidity 71%. Final heating 31, 32 kilowatts, something like that. And we are left with 25 and 50 as our outlet conditions. Okay, great. Let's switch over to our lab document, and we're just going to do a little bit of work and data just to analyze what's happening inside of these components. Okay, so we saw our air conditioning plant had a couple different operating modes, winter and summer. We're just going to look at winter operation first, and then we'll take a look at our summer operation after. So in winter, first question, what are the required operations to bring our cold air, -5 and 60, to 25 degrees and 50? So let's just go back to the simulator page and take a look. So we had our intake air, and it passes through our system sort of that way. Okay, so what we have is, first of all, we have a heater, we have a spray humidification system, and then we had a final heater in order to finally condition our air. Okay, so say here, so we had preheater, we had humidification, and then we had final heating. Okay, and where are we using steam? Well, we're using steam in all of those. So the preheater, yep. The humidification, so we're pre-warming the water that's being sprayed in. And yes, we also need it for final heating. So steam's pretty critical for our processes here. Okay, so we've got a few different processes. What we're going to do next is we're going to plot them on our psychrometric chart. Okay, so I have a psychrometric chart here. And what we're going to do is, first of all, figure out where our points are. So my first point, so a dry bulb temperature of -5 brings me well onto the left hand side and relative humidity of 60. So my 60 kind of comes down, my dry bulb of 5, and I think I end up somewhere around there. And that's my point number 1. Point number 2, I'm at 19.5 degrees dry bulb and 11% relative humidity. So I'm out here is my point number 2. Point number 3, I move up a little bit to about 70% relative humidity and 19 degrees, and that brings me about to here, and that would be my point number 3. And finally, I get to point number 4, 25 degrees dry bulb and 50%, which is somewhere around here. So if I plotted my pathways, what I have is my first point here, which is my preheat. Notice what happens here is that my temperature increases as I move to the right, and my total humidity, which is measured in the vertical axis, doesn't change. So it's essentially a horizontal line across. So I didn't add any moisture. However, because the temperature went up, the hotter air could hold more moisture, so my relative humidity tended to drop. Okay. My next stage from 2 to 3 was where I was adding humidity, so that's where I humidified. So I sprayed in water, which could be now absorbed into the warmer air. And then once I've done that, I had my final heat to bring myself to my comfort conditions. And in general, on this diagram, you know, I'm trying to, I should do a different color. Ooh. I'm trying to target essentially an area that's, I don't know, say somewhere in this range as my comfort conditions. So say 20 to 25 degrees and 40 to 60% humidity. So bringing me into that comfort condition. Okay. We can't just humidify first because that would bring us up right away. So in order to get us to the point where we can humidify, we have to preheat first so that the air is, number 1, above freezing, and number 2, has enough capacity to absorb humidity before it can be, water can be added. Okay, so this was our typical winter heating processes. All right, let's talk about summer. So what were my operations in order to get my air at the summer conditions, 30 and 90, to my comfort conditions? Okay, so let's take a look at our simulator screen again. In this case, started out coming in at 30, and I came up through my pathway this way, and down and around. So I had refrigeration, and I had heating. Okay. Oops. So I have refrigeration, and I have heating. Somewhere my humidity drops. which means I need to likely remove some moisture. So let's figure out where moisture is being removed. So even though I went from a relative humidity of 90 to 100 after the evaporator, that's actually where my humidity or my moisture is being removed. Okay, so we're just going to note that I have this section here, which is a measure of water that is coming out of my system. So as the air, the humid air passes over the evaporator, it cools it enough to remove moisture. And we're going to see that on the psychrometric chart when we plot it. After we've removed the moisture, then we're going to reheat it back to our comfort conditions. Okay, so let's take a look at plotting this on the psychrometric chart. Okay, so let's work at our different points here. Okay, so first point is going to be 30 degrees of dry bulb and 90% humidity. So I'm way up here, 30 and 90. Geez, okay. So that's my point number 1. So I have my 90% line and my 30, which is here. So my intersection point is way up there. Okay, my next point is 13.5 and 100%. So 100% means it's going to be right on the saturation line. And 13.5, so do it from here, so plotting my way up brings me light to here. Okay, so there's my point number 2. And then finally, what I have is point number 3. So 25 degrees and 50% brings me about to here. So that's number 3. Okay, and as we said before, I typically have some comfort conditions that are going to be, you know, somewhat in this range. So that's kind of my target for where I am, and it looks like I've made it to there. Okay, so here's sort of the pathway for that. The trickiest one is, how do I get from 1 to 2? Okay, 2 to 3 is pretty easy. I'm heating, and generally heating pathways go left to right, so that's my heating. Here's what happens from 1 to 2. So I'm cooling, which I guess should be the opposite of heating. So when I leave 1, I go horizontally. So I'm cooling until I get to the edge of my graph. And at that point, what I have now is I've hit my dew point, which means any additional cooling that I do is going to do 2 things. It's going to condense water, so I'm going to create little droplets of moisture that can leave my system, as well as lowering the temperature. So this guy's going to follow along the curve all the way down. Okay. So that's my cooling and dehumidification. It's a lot harder to dehumidify. It's not such a straight pathway. If I was doing my heating, it was just a lot of steps that were bringing me towards my target. This one, instead of going straight down to, you know, my target, has to go end around, and the reasoning for that is that I need to drop my total moisture And the only way to do that, or one of the only ways to do that, is to cool it down till that moisture that's trapped in the gaseous form turns into liquid where I can remove it. Okay, hope that helps clear up some of the applications of air handling and air conditioning units and summer and winter operations, and how we might plot that onto a psychrometric chart.